Hi class. As a follow-up to the previous lecture, which was about sequences, this lecture is going to talk about series. And this lecture is going to be not too big on examples and more just about like the definitions and a little bit of the theory behind it. All right, so what do we mean when we express a number as an infinite decimal? Like for instance, like if we just take pi, what does it mean to write, pi 3.14, blah, blah, blah. The convention behind our decimal notation is that any number can be written as an infinite sum. So here, like it means, 3 plus 1 over 10, because that's the point 1, 4 over 10 squared is 0.04, obviously, and so on. All right, where the three dots indicate the sum continues forever. And the more terms we add, the closer and closer we get to that actual value of pi. All right, so in general, we try to add the terms of an infinite sequence. So we have our sequence a sub n starts at 1 and goes to infinity. We get an expression of the form a1 plus a2, on. All right, so we call this an infinite series or just a series, and it is denoted in short or by symbols. The summation of n is equal 1 to infinity of a sub n, or just the summation of a sub n. All right, so it'd be impossible to find the infinite sum for the series, a sub n is equal to n, just 1 plus 2, because if we start adding the terms, we get the cumulative sums 1, 1 plus 2 is 3, 1 plus 2 plus 3 gives me 6, and so on. And after like the n term, we get what we can write as n times n plus 1 divided by 2, which becomes very large as n increases. However, we start to add the terms of the series. So instead of just a sub n is equal to n, we look at something like 1/2 plus 1/4 plus 1/8 plus 1/6, This just looks like 1 over 2 to the nth power. All right, we get this 1/2, 1/2 plus 1/4 gives me 3/4, 1/2 plus 1/4 plus 1/8 gives me 7/8, and you can see what's happening here. And it ends up just being equal to 1 minus 1/2 divided by 2 to the nth power. That's what the partial sums. All right, so the table here shows that as we add more and more terms, these partial sums, as I just call it, become closer to 1. So like the sum of the first n terms. So as we sum one term, we only get this. 2, after we sum the first 3 terms, the first 4 terms, and as you can see, by the time we sum the first 25 terms, it's like 0.9999999, whatever, 7. We get closer and closer to that value of 1. All right, in fact, by adding sufficiently many terms in the series, we can make the partial sums as close to 1 as we like in this example here. So it seems reasonable to say that the sum of this infinite series is 1 because we keep getting closer and closer to 1. And we can write this as the sum of 1 over 2 to the n is equal to basically 1. So we use a similar idea to determine whether or not a general series has a sum. All right, so what we do is we always consider these partial sums. So like we denote partial sums as S1, that means just the sum of the first term. S2 means sum of the first 2 terms. S3, and so on. S4 is sum of the first 4 terms. So in general, S sub n is the sum of the first n terms, all right? And we write this is equal to the sum, I is equal 1 to n of a sub I. And these partial sums form a new sequence, all right? So the partial sums, we write Sn, which may or may not have a limit. Okay, we're not going to necessarily look at limits just yet. All right, however, if the limit as n goes to infinity of S sub n does equal S and it exists and it's a finite number, then as in the preceding example, we call it the sum of the infinite series, the summation of a sub n. All right, so given that a series, the summation of a sub n is equal to a sub 1 plus let S sub n denote its nth partial sum, as I have shown right here. If the sequence S sub n is convergent and the limit as n goes to infinity of S sub n equals some number S and it exists as a real number, then we can say actually that the entire series, the summation of a sub n, is convergent. And we write a sub 1 plus a sub 2 plus is equal to S. Or basically just the summation as n goes to 1 to infinity of a sub n is equal to S. And the number S is called the sum of the series. So if this sequence S sub n is divergent, then we just call it a divergent series. So like the sum goes to infinity or something. All right, thus the sum of the series is the limit of the sequence of the partial sums. All right, so when we write the summation of n is equal 1 to infinity of a sub n is equal to s. What we mean that by adding sufficiently many terms of the series, we can get as close and close as we like to this number s. So basically notice then also that the summation of n is equal to 1 to infinity of a sub n. Another way we can write it is the limit as n goes to infinity of I is equal 1 to n of a sub I. This is just the series shown in limit notation. All right, an important example of an infinite series is what we call a geometric series. And a geometric series is a plus a sub r plus a sub r squared plus a sub r cubed, da, da, da. And what you can see is going on here is that we're multiplying each term by r, right? And so the nth term is just expressed as ar to the n minus 1. And this is where a is not equal to 0. So it's just the sum starting at 1 to infinity. All right, each term is obtained from the preceding one by multiplying it by its common ratio r, which is great. So if r is equal to 1, then really, so r is just the number 1, then s sub n is just a plus da, 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 which is equal to n times a, which as we take the limit just goes to positive or negative infinity, just depending on what a is. All right, since the limit n goes to infinity, s sub n doesn't exist, we can say then that the geometric series diverges in this case. If r is equal to 1, this geometric series here, all right, diverges. All right, if r doesn't equal, all right, so it's something else. If we look at the partial sum s sub n, it's just a plus ar squared all the way to ar n minus 1. Now, if we look at something called r times s sub n, so it's just the ratio times the nth partial sum, we see this, okay, because r times a gives me ar. And I lined it up this way for a very specific reason. So what we're now going to do is actually subtract these equations. So you're going to take s sub n minus r s sub n. You're going to notice that all this stuff cancels out, and you're just left with a minus a sub rn. Well, factoring out s sub n, which is the partial sum, we get s sub n times 1 minus r, dividing this over. So for these geometric sequences, this is what I'm saying, that are like this, right? Or these geometric series, sorry, that are written like this. As long as r doesn't equal 1, the partial sum, whatever, is always equal to a times 1 minus r to the n divided by 1 minus r. So if I want like the fifth partial sum, I would just replace n with 5 and r with whatever the ratio is. All right, so if r is between -1 and 1, we know that as r raised to the nth power goes to 0 as n goes to infinity. So if it's between -1 and 1, the limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of a times 1 minus r to the n. Here I'm just splitting this fraction up like this, all right? So it's equal to a over 1 minus r, right, because that's this part, minus a times r to the n, 1 minus r. Well, the limit as n goes to infinity of that rn part, this just goes to 0, and you're just left with a over 1 minus r. All right, so thus when the absolute value of r is less than 1, the geometric series is convergent, and its sum is always a divided by 1 minus r, always. All right, so if r is less than or equal to -1 or greater than 1, this sequence r to the n is divergent, and so by equation 3, we can say that the limit as n goes to infinity of s sub n, it just doesn't exist. All right, therefore the geometric series diverges in most cases, only it's convergent when the ratio is like this, between these two numbers. All right, so we summarize the results of example 2 as following. So the geometric series, the summation of n is equal to 1 to infinity of ar n minus 1, is convergent if the absolute value of r is less than 1, and its sum is this right here. And if the absolute value of r is greater than 1, then we just say the geometric series is divergent. It just shoots up forever. All right, so let's talk about this harmonic sequence that we call it, or harmonic series, excuse me. The summation of n is equal to 1 to infinity, so 1 divided by n is equal to 1 plus 1/2, so on, is divergent. All right, so for this particular series, it's convenient to consider how the partial sums S2, S4, S8, S16, S32, and show that they continue to become large. So S sub 2 is equal to 1 plus 1/2. S sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. But I know that this sum here is greater than 1 plus 1/2 plus 1/4 plus 1/4. Right? There's a reason to this madness here. All right? And that's equal to 1 plus 1 divided by 2. So it's greater, S sub 4 is greater than 2, basically, is what I'm saying. So if I keep doing this, S sub 8 is 1 plus 1/2 plus 1/3 plus 1/4 plus da, 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 da. Well, S sub 8 is greater than, if I make this a little bit more convenient, change the 1/3 to 1/4, all these to 1/8. All right, this is 1 plus 1/2 plus 1/2 plus 1/2, all right, which is 1 plus 3/2, right? So it keeps getting larger, is what I'm saying. Same process with S sub 16. It's 1 plus 4 over 2. So it keeps getting larger and larger and larger and larger. All right, similarly, you can see for S32 and S64, and in general, S sub 2n is greater than 1 plus n divided by 2. All right, so then this shows that S sub n by 2 goes to infinity as n goes to infinity. So my partial sums of S sub n, they're divergent. All right, so that harmonic series there diverges and it just doesn't converge. It goes to infinity. All right, finally, if the series, not finally, another theorem here. If the series, the summation of n is equal 1 to infinity of a sub n is convergent, then the limit as n goes to infinity of a sub n is equal to 0. Interesting. All right, so if it's convergent, its limit as a sub n goes to infinity is equal to 0. Basically, what that means is the nth terms aren't adding anything to the sum. So the converse of theorem 6 is not true in general. So if the limit as n goes to infinity of a sub n is equal to 0, we cannot conclude that the summation is convergent. So only convergence guarantees that the limit of a sub n as n goes to infinity equals 0. So a test for divergence here. If the limit a sub n as n goes to infinity does not exist, or if the limit as n goes to infinity if a sub n does not equal 0, then the series, that's infinite sum there, all right, is divergent. So the test for divergence here follows from theorem 6 because if the series is not divergent, then it's convergent. And obviously, that limit would have to be 0. All right. We'll end on here just with some basic theorems of summations. So if the summation of a sub n and the summation of b sub n are convergent series, then so is the series, the summation of c of a sub n, right? And the summation of an plus bn and the summation of an minus bn. And then you also have the following. So just like with any basic algebra, you can factor out a constant, you can evaluate these two sums separately, and you can evaluate these two subtractions.